everyone to the afternoon session of the LMS Bar Symposium on the Mathematics of Machine Learning. It's my pleasure to introduce Yuejie from Carnegie Mellon University, who's our next speaker. She's an expert on the foundations of data science, machine learning, and inverse problems. She has received numerous awards already in her quite short career so far. And there are actually so many that I won't even list them. But most recently, she was a plenary speaker at this year's SIME Imaging Conference. So now I'm very excited to hear more about your recent work.
Okay, thank you so much for having me today, and thank you so much for the introduction. So today I'm actually going to talk about sort of a new line of work that we recently started in our lab on reinforcement learning. Particularly, I'll talk about fast global convergence and natural policy gradient methods with entropy regularization. Okay, so this is joint work with two fantastic graduate students, Shizong Chen from my group and Chen Chen from Stanford, and also Yuxin Chen, who is currently assistant professor at Princeton EE, and my colleague Yuting Wei, who's an assistant professor at the stats department at CMU. Okay, so the focus of this talk is on reinforcement learning, where an agent tries to learn by interacting with the environment. Reinforcement learning is typically thought as a form of machine learning that is closest to human learning or nature learning, and it has a lot of unique challenges compared to, for example, the supervised learning setting, which we are all quite familiar with. In particularly in reinforcement learning, the environment that the agent is interacting with is typically unknown, can be very complex of high dimensionality, and sometimes can also be changing over time, so it's non-stationary. The agent is typically also not only just interested in its immediate world, but actually is a cumulative award in the long horizon of the problem. So therefore, because of this delayed feedback or rewards, the agent typically needs to exploit the environment in a trial and error manner, resulting in the so-called exploitation and exploration trade-off that is well known in the reinforcement learning setting. Okay, so despite all these challenges in reinforcement learning, in recent years, there has been a lot of success stories of reinforcement learning that hits the news headlines, such as in applications of games, robotics, motor controls, and so on. In most of these success stories, policy optimization, particularly when coupled with using deep neural networks, has been a major driving force towards these successes. In this talk, we are also interested in understanding policy optimization, particularly in the context of a tabular MDP setting. As a mathematical workshop, let's look at some mathematical formulations, how to formally formulate this policy optimization problem in an MDP setting. Okay, so MDP, a Markov decision process, there's a very well studied and popular model to model the interaction between an agent and the environment. We model the status of the environment using a state space. For example, a state can be the current stone configurations in a Go game. Similarly, we model the actions of the agent using an action space. For example, an agent can take an action from the action space corresponding to where to push the next stone in a Go game. Okay. Now, after taking an action, the agent will receive a reward from the environment, which is a function of the current state and the current action is taking. And this will also force the environment to transit to the next state, where the state transition is governed by a state transition kernel, which is a function of the current state and the current action. Okay. Now, because of the Markovian nature of the problem, where this transition only depends on the current state but not the history states, it's sufficient to think about a policy, which is action selection rule of the agent that solely depends on the current state of the MDP. Okay, so essentially, you can think of this policy pi when fixing the state describes the probability distribution over the action space. Okay. Now, how do we evaluate whether a policy is good or bad? To do so, we introduce the so-called value function of a policy. Essentially, imagine that we execute a policy pi over an MDP that starts at some initial state S. And by executing this policy, we get a collection of a sequence of rewards from this trajectory. And the value function essentially look at the expected long-term discounted reward from the trajectory. Okay, so similarly, we can also define the state action function, Q, which is also known as a Q function, which is essentially quite similar to the way we define the value function, except that we are going to fix the first action as fixed as A, rather than taking from the policy, while the ensuing actions will be following from the policy pi. Okay, now by considering a discounted reward, essentially what we mean is that we are going to value more about the near-term rewards rather than the sort of rewards that are further away in the horizon. This discounting parameter gamma essentially dictates what is the horizon of the problem we are interested in. So effectively, you can think of the factor 1 over 1 minus gamma, which is the sum of this geometric sequence, sort of determines the effective horizon of this problem. So for long horizon problems, the parameter gamma will be sort of set to a number that is very close to 1. Okay, now with this value function in place, we can formally define the goal of a reinforcement learning problem as finding the optimal policy that maximizes the value function. If we know what the environment is, if we know the probability transition current and the reward functions, this problem falls into the classical realm of dynamic programming and optimal control that has been studied for decades. On the other end, if the environment is unknown, this falls into the realm of reinforcement learning, where we must learn about the environment through interactions. Now, in this talk, we are going to be interested in a class of optimization methods that try to find this optimal policy. Now, in order to invoke an optimization method, we need to first define what the objective function is. So a natural idea is that we can aggregate the vector valued value function into a scalar form by aggregating it over an initial state distribution called rho. Okay, with this we effectively obtain a scalar valued value function called v pi rho, and then we can just try to search for policy pi that maximizes scalar value function. In practice, it is quite popular that we consider a parameterization of this policy called softmax parameterization. The benefit of using a softmax parameterization is that it allows us to easily handle the constraints that the policy pi must be lying in the probability simplex in the action space. In addition, the gradient of the softmax function is quite easy to calculate and emit some appealing forms. Okay, so with this being said, we effectively convert the parameter of interest pi into theta and can rewrite the optimization problem as a problem about optimizing the parameter theta instead. Okay, and with this in place, we are ready to introduce the class of method called policy gradient method, which is simply running gradient ascent on the parameter theta using the gradient, the value function with respect to theta, where eta is some learning rate. Okay. So typically, this vanilla form of the policy gradient method is typically being boosted by some other algorithmic ideas that has been popular in practice. So in this talk, we'll be focusing on two types of boosters that improve the performance of the vanilla policy gradient methods. So the first idea is to use natural policy gradient instead of policy gradient. So what this natural policy gradient does is nothing but just apply a preconditioning factor to the gradient, where this preconditioner is defined as the inverse of the Fisher information matrix that depends on the parameterization of the policy. Okay, so with the introduction of this preconditioning operation, effectively this ensures that our update for the policy pi is invariant regardless of what parameterization you are using for it. Optimization-wise, this often leads to a better geometry that makes the optimization more efficient, something we're going to illustrate shortly. Another important algorithmic idea is called entropy regularization. So what this entropy regularization does is that it would like to encourage exploration by promoting the stochasticity of the policy being used. So the way to do this is to adjust the instantaneous reward in the definition of the value function by adding an actual regularization term that look like on the other log policy. Okay, so by adding this regularization term, effectively we are punishing policies that are being deterministic, and would like to encourage the policy to take some non-zero values. Okay, so we're going to call this parameter tau our entropy regularization parameter, sometimes also known as the temperature in the reinforcement learning literature. And the resulting value function, the resulting regularized value function is going to be called the soft value function. Now with this change, all we need to do is just to replace the objective function in the earlier introduced policy gradient or natural policy gradient methods by replacing the objective function to this regularized version. Okay, so before we continue, let's just look at a simple toy example to illustrate how these algorithmic ideas help to accelerate the optimization procedure. So in this picture here, we are showing sort of the optimization landscape, all the gradient flows of either using policy gradient methods or natural policy gradient methods for a toy bandit problem with 3 arms. And we are sort of just plotting the trajectory of the policies in this picture. And when we move from the first row to the bottom row, we're increasing the regularization parameter tau for both methods. Okay, so clearly we can see that by comparing policy gradient to natural policy gradient, we can see the natural policy gradient flow tends to points towards the optimal policy through a more direct path compared to policy gradient. And therefore, it's hopeful that we can get a faster convergence. Similarly, when we increase the level of entropy regularization, we can see that the trajectory of the optimization algorithm also improves and seems to lead to a faster convergence, albeit to a slightly different optimization objective. Okay, so with this intuition in place, indeed, if we now turn to what people use in practice, there is no shortage of examples where this policy gradient methods has been quite advantageous in applications. Some of the reasons might be due to the fact that compared with some other classes of methods that search for the optimal policy, such as using value-based methods, the policy gradient methods directly optimize the policy of interest, the policy which is a quantity of interest. It also allows a flexible integration with neural networks by, for example, using a neural network to parameterize our policy. Indeed, some of the most popular methods that has been used in practice, such as trust region policy optimization methods, the TRPO method, is nothing but a natural policy gradient in conjunction with length search. On the other end, turning to entropy regularization, it has been noted in some of the early landmark papers by DeepMind and Berkeley, a group from Berkeley, that indeed using entropy regularization can greatly improve the exploration of the policy and leads to better algorithms. So despite this empirical evidence, on the theoretical end, our understanding of policy gradient methods has been severely lacking, partly due to the fact of the associated non-concavity of the associated value maximization problem, which is true even for the simple toy problem we just illustrated. Nonetheless, there has been some very nice breakthroughs in the literature that people try to understand the global convergence of policy gradient methods for some class of control problems such as LQR or tabular MDP problems, with or without entropy regularizations. So this precursors has motivated our study for the entropy regularized natural policy gradient methods, which is the focus of our work. Okay, so let's now focus on the entropy regularized NPG methods. In this work, we have been focusing on the tabular setting, which interestingly, in this setting, the update rule can be actually expressed in terms of the policy in a fairly simple form given on the slide. Okay, so let's try to pass this update rule a little bit. So effectively, we can see that we are effectively updating the policy using sort of a multiplicative combination of the previous policy and the soft greedy version of the value function of the previous policy. So pictorially, we can run this algorithm in a way that, let's say we are given an initial policy, we can start by evaluating the soft Q value of this policy, and then do a sort of soft greedy operation through this exponential map, and then combine this with the previous policy. Okay. Now, if we set the step size eta to the largest possible, that is 1 minus gamma divided by the regularization parameter tau, effectively we can drop the influence of the previous policy in the first term and only keep the soft greedy term. And this leads to an algorithm that is known as soft policy iteration. That is basically a soft version of the classical policy iteration algorithm people have in dynamic programming. Okay. Now, this update rule is also invariant regardless of the choice of the initial state distribution rule we are using. We are going to also call that the optimal policy as pi tau star, and also the optimal Q value as Q tau of star as a shorthand notation. So to study the convergence of this algorithm, we begin with a case where we can perfectly evaluate the soft value function given the current policy. This can be achieved, for example, when we have perfect knowledge about the model of the MDP, such as in a classical dynamic programming setting. Okay. Our theorem says that for the entire range of the learning rate, from 0 to 1 minus gamma divided by tau, this entropy regularized NPG updates always converge linearly, achieve linear convergence for the soft Q values in terms of L infinity null. With the introduction of the entropy regularization, we can effectively guarantee the uniqueness of the optimal policy and also talk about convergence of the policy directly. So our theory said that we can guarantee that the log policy achieves linear convergence also in the L infinity norm at the same rate as the Q value function, except the leading constants is a little bit different. Okay. Now, one remarkable feature about this result is that there is no hidden constants whatsoever in the result. Now, to illustrate the result a little bit further, let's zoom into the convergence result for the Q values and consider how many iterations we need in order to achieve epsilon accuracy to recover the optimal regularized Q function. Okay, so to achieve this epsilon accuracy, if we are using a general learning rate, the iteration complexity essentially scales on the order 1 over eta tau times a log factor about 1 over epsilon. Okay, so if we fix eta as some constant, small constant, the convergence rate, the iteration complexity essentially scales as 1 over tau, which means that as we increase the regularization parameter tau, the number of iteration we are going to take will reduce. Now, if we, this convergence rate will be maximized when we take the largest possible step size when eta equals to 1 over gamma, 1 minus gamma over tau, leading to a contraction factor that is independent with respect to the temperature tau, where the iteration complexity essentially scales as 1 over 1 minus gamma times log 1 over epsilon. Okay, so a careful listener may realize that this iteration complexities actually do not depend on the ambient dimension of my MDP, especially the dimension of the state space or the action space, which can be huge. Okay, so effectively, this illuminates a very encouraging message about the convergence behavior of entropy-regularized NPG method, such that it actually converges at a dimension-free rate, which can only depend on the so the dimensions of MTP, maybe in a logarithm factor that are hiding in these factors. But beyond that, it's almost dimension-free. Okay, so a natural comparison is to try to compare its performance with unregularized MDP when there is no entropy regularization. So this is a setting that has been studied by one of the pioneer work in the field by Agavo et al. Last year. In that setting, they also show that vanilla NPG method also achieves a kind of this dimension-free convergence rate, that where the convergence rate does not depend on the dimension of the MDP. However, the convergence rate for the vanilla NPG method only scales sublinearly with respect to epsilon, where the convergence iteration complexity is on the order 1 over epsilon. Now, in contrast, our studies show that this regularized NPG methods achieves linear rate of convergence, where the iteration complexity only depends on epsilon on the order log 1 over epsilon. Okay, this suggests that even with a small amount of entropy regularization, it helps to enable fast convergence for such policy optimization problems. Okay, so far we have only talked about the case where we assume we have perfect knowledge about the policy evaluation procedure by assuming access to an oracle. Now, in the approximate setting or reinforcement learning setting, we typically do not have perfect evaluation of the value function, leading to our consideration of an inexact oracle, which we assume this will return a policy evaluation that is only accurate up to some accuracy delta in terms of the L infinity norm. For example, this can be done by combining with some sort of sample-based estimators for the for policy evaluation, and can be guaranteed as long as the sample complexity is high enough. Okay. Now with this inexact oracle, we can modify our update rule for the entropy regularized NPG method by replacing the exact Q function to this inexact version, and ask the following question: does this modified inexact version of the entropy regularized NPG still achieve fast convergence with respect to the imperfect information about the policy evaluation? Okay, so encouragingly, our message is positive. Essentially, we can show that this method still achieves the same iteration complexity as previously said, as long as the parameter delta is sufficiently small that is on the order of some constant, some pre-constant times the epsilon, which is the accuracy we would like to achieve. The pre-constant that we show here, again, does not depend on the ambient dimension of the MDP, except the discount parameter gamma and the learning rate. This tolerance level is going to be, again, maximized in the setting where the step size is set at the largest possible, leading to the following tolerance level where delta roughly scales on the order epsilon times 1 minus gamma to the square. Okay, so with all the theories that are being showed, now I would like to maybe spend just maybe 2 or 3 minutes on sort of what's the analysis we are using. Particularly, one of the interesting tools that we use in the analysis is what I think is a soft version of the very well-known Bellman's equation. So to begin, let's recall what the Bellman's operator is in the classical setting of dynamic programming. What the Bellman operator does essentially is that it allows us to basically guarantee a fast linear convergence of the classical value iteration or policy iteration algorithm through 2 key properties. Okay, so the first key property is the so-called Bellman equation, which shows that the optimal Q value is the fixed point of this Bellman equation. Okay. Now, on the other end, the Bellman operator is a contraction operator in terms of the infinity norm, where the contraction rate is exactly the discount factor gamma. Okay, so with these 2 key properties in hand, it's very straightforward to show the linear convergence of policy iteration. Now, it turns out that in this entropy regularized version of the problem, what we are dealing with effectively is a soft version of the Bellman operator, which we define in the paper. Effectively, all this soft version of the Bellman operator essentially takes into account of the entropy regularization. Interestingly, the most important message is that it inherits many of the key properties of the original Bellman operator. For example, we can show that the optimal soft value function is in fact the fixed point of the soft version of the Bellman equation. In addition, this soft Bellman operator is also a gamma contraction in terms of the L infinity norm. So with these key properties enhanced, in fact, we can show the convergence of soft policy iteration, which is a special case of our entropy regularized NPG method as a largest step size in a fairly straightforward way that essentially mirrors the proof of policy iteration in the classical domain. All we need to do is just replace the Bellman operator by the soft version of this Bellman operator and show the contraction where the soft policy iteration achieves exactly the same contraction rate as a policy iteration algorithm in the classical setting. So this essentially establishes this mirror relationship between the entropy regularized MDP problem with the original unregularized MDP problem in the classical dynamic programming setting. Okay, so with that being said, I would like to conclude my talk with a few remarks. So the key idea, the key message in this talk is that we have established that the entropy regularized NPG methods achieve a fast global convergence for tabular discounted MDP, where the convergence rate effectively is almost dimension free with respect to the ambient dimension of the MDP. This work opens up several interesting future directions. The first direction is that we have been presumably just restrained ourselves to the tabular setting, while in practice, typically, these methods are used in conjunction with function approximations such as neural networks. Therefore, it will be interesting to study how these convergence results behave when we use function approximators. It might also be interesting to think about analyzing sample complexities of these algorithms when combining with statistical methods to estimate the value functions, such as in a context for the soft actor critique algorithms. With all that, I would like to conclude by thanking our funding agencies, without whom we will not be able to carry out this research. With this, I'll conclude, and thank you so much for your attention.